Okay, so yesterday we stopped when we were talking about water having a high heat of vaporization, which meant that it took a lot of energy in order to convert it into water vapor. And then we also talked about water having a high heat of fusion, which meant it took a lot of energy. You had to remove a lot of energy for water to turn into ice. And I think I wrapped things up by showing you a little chart that under the conditions on Earth, water is basically a very stable liquid. So today we're picking up with the next property of water, which has to do with what happens when water freezes, and that is the fact that ice floats. When we think about ice floating, everybody pretty much knows that ice floats. But you may not have ever thought about the fact that that's actually extremely unusual. Because if you were to take, for example, a big iron block and melt it, and drop a piece of solid iron into it, it would sink. If I was to freeze a block of alcohol and then drop that solid chunk of alcohol into liquid alcohol, it would sink. So it's very unusual. In fact, one of the very first things that you learn in chemistry is that solids are tightly packed, and then liquids are more spread apart, and then gases are really spread apart. So this sort of goes against that, because what actually happens is in water, ice is actually less dense than water. Solid water is more spread out than liquid water. Water is actually the most dense at about 4 degrees Celsius. At what temperature does it actually freeze?
0.
At 0 Celsius. So as it's dropping in temperature, it's actually getting more dense at first. But then when it gets to about 4 degrees, that's the most dense. What's going to happen is water, as it's cooling, is actually going to sink and bring warm water up. So in one way, organisms are going to be protected because the water's going to keep moving. It's going to keep the temperature balanced. But then, even when the water in the top layer does start to cool below 4 degrees, and now it's getting lighter and it ends up at the top, that means that the lake is actually going to freeze from the top down. Ice is going to insulate the organisms underneath and form a layer on the top. If it was the other way around and ice sank, then what would happen is you would end up with a lake freezing from the bottom up, which would mean that all the organisms would freeze. So the fact that it freezes on the top and floats is actually a good thing, because now it's going to protect the organisms that are under the water.
Isn't the water still freezing?
It's cold, but it's not freezing.
Frozen.
Right, and the thing is, in your cells too, if we take a cell like cryogenics and we try to freeze it, if the cell actually freezes, what ends up happening is ice is very sharp. So when it starts to freeze, you get these little sharp shards of ice, and then and when you defrost them, like they try to do with mice or whatever, the shards of ice have poked holes in all the cells, in all the cell membranes. So then even when you defrost them, they don't survive. So the fact that ice floats is going to keep everything else just above that freezing temperature. So even if it's a cold-blooded organism, it's gonna cool, but not to the point where it would actually freeze. So that's really important. Organisms that live in places where it's colder than freezing, actually we've discovered, you may know this, that they actually have a like an antifreeze, the equivalent of antifreeze in their system, so that their temperature can actually go below 0 without forming ice. And that's actually, if we were going to go into the whole cryogenics thing, that's actually what they're thinking about, is could we inject something that would be non-toxic that would allow the cells to get that cold that everything slows down and you could put them into preservation, but without forming those sharp shards of ice that would then puncture the cells when you defrosted them. So this this next thing is actually an explanation of why ice floats. So in order to understand this, we have to go back for a second to the structure of water. So if you remember water structure, what kind of bonds hold a single molecule of water together? These little sticks here, what kind of bonds are those?
Hydrogen.
Not hydrogen, be careful. These bonds. I thought I heard somebody say that. These are covalent, not just covalent, but the uneven type of, very good. The uneven type of covalent, which is called, I heard somebody just say it, polar covalent.
Yes.
And because of that, we end up with these partial charges. This is our oxygen. What kind of partial charge does it have? Positive or negative?
Negative.
Partial negative charge, because oxygen has all those electrons around it, and then our two hydrogens end up with these partial positive charges. And that's what causes the attractions between them, and that's the hydrogen bonds. The thing is, in liquid water, if we imagine this is a hydrogen bond between one water molecule and another water molecule, what's going to happen here is that this bond is going to form, but it's really, remember, like Velcro. It's just a strong attraction. It's going to form for a fraction of a second, and then it's going to break. And then the water's going to form it with another one. So when that bond breaks, here's the thing. When this bond breaks, this can now slide past, and they can get very close to each other. And then another one forms, and then it breaks, and they slide past. So when the hydrogen bonds form, yes, it's causing them to kind of stick together, but it's causing them to stick together at a specific distance. In other words, a hydrogen bond has a certain length to it. Here. Oops, here. And that's basically as close as they can get when it's hydrogen bonded. Now in a liquid, it doesn't matter, because like I said, those bonds are lasting for a fraction of a second, and then the molecules are sliding past each other. But what's going to happen when it becomes ice is that these hydrogen bonds are going to lock in place. So believe it or not, even though it's going to freeze into a block, what's actually going to happen is the hydrogen bonds are going to force it. When it freezes, the molecules are actually going to be slightly further apart than if it was a liquid and those bonds were being made and broken and the molecules were sliding past each other. And this is why if you leave a soda in the freezer for too long, it explodes. If you do it with water bottles, same idea. When you do it with a water bottle, you may come back and find the bottom of your bottle's all bulged out. It won't stand up anymore. And that's because solid water actually takes up more space than liquid water does. And so, which is a very unique property. And like I said, in the case of life, it insulates organisms below the surface when water freezes on the surface of lakes and things like that. So, any questions about that property of water? Okay. This is just showing a diagram. You don't have to know that there's a honeycomb structure, but this is the honeycomb structure they're referring to, that when those hydrogen bonds lock in place, the water molecules are sort of forced further apart than if they could actually slide past each other. And this diagram, I don't know if you've ever seen phase change diagrams in chemistry. You might have. This is basically showing different combinations of temperature and pressure. Pressure for us on this planet right here, this is where we are. We're at sea level, so it would be around here. And then water on this planet is going to be somewhere between typically 0 and 100 degrees. Hopefully it's not 100 Celsius anywhere, because that's boiling. But the bottom line is, if you notice that basically on the conditions of our planet, water is the perfect liquid. It's a liquid, in all of this range. On another planet, it might all be frozen or it might all be gas. But on our planet, it's a liquid because of its structure. Okay. This last section on the pH scale is actually coming from the notes above the water notes. If you slide back to basic chemistry, I did this online, but I did such a very, very quick explanation of it that I wanted to go over it again. So if you go to the paragraph just above water, and it talks about pH from the basic chemistry lecture, that's where we're at right now. So pH scale. In chemistry, particularly if you take AP chemistry, you have to learn a lot about pH, and you have to actually understand how a log works on your calculator, and you do a lot of calculations with pH. In here, you don't have to know all of that. All you really need to know is that even though water is covalent, polar covalent, little bits of water do break up on a very, very, very small scale. And if water breaks up, we can write water not just as H2O, but you could write it this way. You could write it as HOH. Now acids, which is coming up in a few minutes, acids tend to make hydrogens in solution. So acids, something like hydrochloric acid, when you put it in water, it releases a bunch of H's. And that's what causes the pH change, the pH below 7 making it an acid. And bases tend to do the opposite. They tend to either pick up hydrogens or they release hydroxide, OH. The thing is, since water is HOH, even if a water breaks, you're not going to have an increase in hydrogens without an increase in this also. In other words, when water breaks up, it's not going to make an acid or a base because it does both. It makes a hydrogen, which is what acids do, but it also makes a hydroxide, which is what bases do. So water, even though it can break up a little bit, is completely neutral. And that's where we get our neutral pH from. So here's what you need to know, or the first thing you need to know. What is pH? Well, it's calculated using the log function on your calculator. It's the negative log of the hydrogen concentration. The good news for our class, you're not going to need a calculator. You don't even actually have to understand what a log is. Okay, so you don't have to understand log because in our class, if you're asked for the pH of something, they're going to give you a hydrogen concentration that's a whole number. So in this particular case, the hydrogen concentration is 10 to the negative 7th. To get the pH, all you do is just take this exponent, and that's your pH. And that's what you need to know about if I gave you a hydrogen concentration, how do you get the pH from there? In chemistry, you would do it, you may need a calculator to do it, but for the purposes of what we're doing, you don't. So pH is just going to be the negative log. So what if the hydrogen concentration was 10 to the negative third? What would the pH be?
3.
The pH would just be 3. Really simple. So it's just the exponent, that's going to be your pH. Now, you probably learned, hopefully, at some point, that the pH is based on a scale of 1 to 14, and neutral is 7, and below 7 is an acid, and above 7 is a base. But one of the things that people don't quite always have a handle on is this. What does pH really mean as far as relating it to hydrogen concentration? If it's measuring how many hydrogens there are in a solution, how do we know exactly numerically what that's going to be and how is that going to change? So the thing is, when the pH goes down by 1, the hydrogens increase by 10. For example, let's say we went from a pH of 7 to a pH of 6. Well, remember that pH was the negative log of the hydrogen concentration. So that means the hydrogen concentration of this would have been 1, 2, 3, 4, 5, 6, 7. The hydrogen concentration of this is 1, 2, 3, 4, 5, 6. This is actually a bigger number. The hydrogen concentration actually went up even though the pH went down. So if you were trying to figure in your head why is the pH going down but the hydrogens are actually going up, because remember, pH is sort of a shortcut. You don't have to know this as far as calculating, but if I do tell you that the pH changed from, let's say that I tell you the pH changed from 10 to 8, and I ask you by how much did the hydrogen concentration go up, what do you think?
20%.
Sometimes I hear 2, sometimes I hear 20. Neither one of those is right, by the way. 100.
Oh.
Here's the thing.
Close.
We went from 10 to 9, so it increased by 10. When we go from 9 to 8, it increases by 10 again, meaning the decimal is going to move 2 places. It's actually increased by 100. So that's what you have to know, is that when I say that every drop raises the number of hydrogens by 10, I could say, oh, the pH goes from this to this, by how much does the hydrogen concentration go up? You need to know that all you're going to do is just count the jumps and multiply by 10, because it's going to be 10 times 10 times 10, and that's how much it's going to go up. If you're going the other way, that's how much it's going to go down. Hydrogen goes up, hydrogen goes down as the pH goes up. Does that make sense? Okay.
This is on your video on YouTube, right?
This is, I'm making it now. Your voice will now be in it. Yes. So touching. All right. At 7, we have neutral. Below 7, it's an acid, and above is a base. Most people already know that. You do need to know that. So acid and base, and that the drop goes up by 10, and that the definition is the negative log of the hydrogens. And the very last thing that you need to know, and then I'll show you how I could apply this information, is that pH and pOH add up to 14. So here's an application question. Here's what I might actually ask you on a test. I could give you 4 choices. I could say we have a pH of 4, choice 2, a pOH of 12, choice 3, a hydrogen concentration of 10 to the negative 6, and choice D, an OH concentration, a hydroxide concentration of 10 to the negative, let's say, 10.
Oh.
Sorry. And then I could say, which of those is the strongest acid? That's my question. Which of those is the strongest acid? Well, here's the thing. If you want to know which one's the strongest acid, I hear some people saying C, you need to put all of those in the form of pH, because we know that as the pH goes down, that's a stronger acid. So whichever one has the lowest pH is going to be our answer. So we already have the pH on this one. The pH on this one is 4. The pH and the pOH add up to 12. So what's the pH on B?
2.
So the pH on B, oops, meant to do that in pen. Yes. The pH on B is 2.
It adds up to 14.
How about on this one? The pH on this one is 6. And now what about this one? 4, because if the OH is 10 to the negative 10, that means the pOH is 10. Since pH and pOH add up to 14, the pH would be 4. So which one of those is our strongest acid?
B.
Choice B is actually our strongest acid. I think you said C.
No, it's like-
Yeah, we'll play it back.
That was me.
Wait, Miss
I
Coleman.
said